In English, I'll continue speaking in English. First, I would like to thank for the opportunity to speak here and for everybody coming to listen. I'm talking about the work joined with the Erel Avineri, and also I would like the chance to thank him for bringing me into this research. I'm a mathematician. This is my world. I'm not used to speak in transportation area, but he came up with the idea and started to talk, and it was a very enjoyable collaboration. So this is a chance to thank Erel. What I'm talking about is multi-class graphic user equilibrium model. So our motivation for the problem is traffic equilibrium. So one of the things that come up is that we have a link that we have a route of transportation, and at some point we have choices of where to choose to which route we want to go, and this is and at some point you have to choose to go right, to go left, and after a while, after you went for some choice, we get to this situation that nobody has an interest to go from one direction to the other because the time it takes to go from one point to the other is the same. How does it affect the world? So we have here different motivations, for example, prediction of travel time, investigating large complex networks. For example, one of the origin for our problem was the case of glass orbitals, where the addition of one link leads to a higher time equilibrium on the network. What we tried to do, what we did, and what we started to do is consider multi-class traffic user equilibrium, meaning that in classical user equilibrium cases, we consider all cars, all translation of one class rather than different classes. For us, we consider the case that we have different classes affecting the time. So, for example, the first example that came up to mind was that we have high goods vehicles against private cars. They affect differently on the time that it will take to go from one point to the other, or public transportation compared to private cars, or usually regular cars and autonomical vehicles. This is something that I actually feel that happens to me every day. Well, not every day, because usually I choose public transportation and I let the driver take care about the time. But in the unlikely event that I go from Africa home, I live in Ramat Gan, I get to the choice, to the point that I have to decide. Do I go from Yank Street or do I go from Krenitzi? And well, it depends on how much cars I see and how much public transportation, for example, I expect to see, or how many. I know that if I see a big car, or in the morning, if I see the cleaning car choosing one route, I know that I want to go from the other direction because it will affect my time. One of the things, well, here we have an example of a lot of different vehicles affecting the time that it will take. So we have the coast, we have the camels, we have the pedestrians, we have the cars. And one of the assumptions on our model was that once you chose one direction, you cannot pass other cars. Once again, something that will happen to you if you go to Bialik Street in the afternoon, because well, so many cars you can't choose to go through. unless you go by a motorcycle. So here is the formulation of the problem that we have. So we have two points that we want to go from. So we want to go from A to B. We assume that we know the demands X1 and X2, and each class X1 and X2, each vehicle from X1 and X2 chooses to go either from the link E1, which is the top one, or E2 from the link from the bottom one. So the sum of X1 and X2 is X1, and the sum of these two is X2. So we have here four parameters, but they are linked in pairs, and we chose the time to be dependent linearly on the parameters, where there are many different types of time dependency on the demand in the literature. Since we just started and I knew the subject, we decided to go with the linear, the simplest one. We chose really the simplest possible model, 2 points, 2 links, but the change here is that we chose two classes. So this is the time. This is the time that it will take you to go from point A to point B. And time equilibrium means that the time on the top equals the time on the bottom, or nobody chooses to go on top, or nobody chooses to go on the bottom because it will take longer. So this is the case of multi-class user equilibrium. So what we found out? Well, everything that we did, we proved analytically, rigorously, and the proof is in the paper, and it is being finalized these days. And what is the result? So we found that there are many. We have the space of all demands. X1 and X2 is the space of all demands. And we saw that there are 5 different sets of demands. For each such set, we can find a different type of time equilibrium. So we calculated the time equilibrium that it will take you to go if we know the demand. And so it looks like that well, this is the set of all demands. And for example, suppose that we have X1, the demand of X1 and X2 that lives in set 2. Then we found what are the possible time equilibrium. We found out that we have, in fact, a range of time equilibrium, meaning that for a range of choices of, for example, X11 between one number and the other, we have a time equilibrium, meaning that nobody has the interest to go from one route to the other, or to choose differently the next time that you get there. And we have, since we have this, we have 2 extremal cases. We have the maximal and we have the minimal. Everything depends on, say, the parameters of the setting of the graph, and given these parameters, we have a range of time equilibrium. From my point of view, I think about it as suppose that you can, as a regulator, control one of the demands. Say that you can choose that one of the routes, the public consultation will not go from one of the routes, but only from the other. You can choose you can control the time equilibrium that will be on that set. And this is in fact the case in set 2, that you can choose the case that the minimal time equilibrium will happen if none of the cars from none of the elements from class 1 will be on link 1 or won't be on link 2. Maybe we can see it in a numeric example. So basically all numbers can be random, and the range of numbers is random. Being a mathematician, I don't care about units, but you might want to take care about units. So think about 4 as minutes, but x1 and b1 are just numbers, say thousands of cars, dozens of cars, or whatever, but we can look at it as just numbers. So this is the case that we chose. These are the parameters of the net. Exactly the amount of time. And here is how we can see the effect of the time equilibrium. So suppose we have elements that lie in set 1, for example, in this case, x1 equals 1 and x2 equals 1, then there is no interest of going through link 2. You can see that everybody chooses to go on link 1 and nobody wants to go to link 2. Say, for example, link 2 is much too longer in this case. But after a while, suppose that we change into the amount of elements grows, for example, in this case, 4 and 3, then we have the best time equilibrium that we can choose is that all of the elements from class x1 will be on link 1 and none of them will be on the bottom one. If at some point we know that we expect bigger demand on from x1, then it affects differently. We can see the different cases, how they affect on the time equilibrium. It will increase, but we can control the case. We have future research intended. We can make the net more difficult. We can do empirical research and many ways to complicate things.
Thank you.